there are any issues with your stay, feel free to come and tell me. Food, anything, really anything. Whatever is possible, we will try to do. Okay. So now we have the second lecture by Professor Sarkar, and you should ask questions because you know that there is a prize waiting. So, and there is only one prize, so you should all compete properly. Okay.
Hey, thanks, Kiran. Okay, so now we move on to the sort of cosmology proper, which is the construction of relativistic world models, and then we'll get on to the physics of dark matter after all this. So we summarized, I gave you perhaps more detail than you're used to about what our universe actually looks like in our neighborhood, and you can see from this is a plot of the actual distribution of galaxies around us. So we are in the middle here, and to set the scale, that's 100 million light years, right? So we have of course mapped the sky in some detail. Astronomers have given the names as you do, and I was referring in the last lecture to the Shapley supercluster. That is this huge conglomeration of clusters of galaxies in the sky, and there are similarly other such superclusters. This is Pisces, Cetus, then the Horologium and so on. So they all have specific names, and they are essentially the largest structures that we see in the universe. So a galaxy, we said, is 10 to the 11 solar masses. Clusters of galaxies can have tens of thousands of galaxies, and then this is a collection of tens of thousands of clusters. So we are getting up to masses of the order of 10 to the 17, 18 solar masses. And basically the question that I want to pose to you is that we are now going to start developing the standard cosmology, which is based on the idea that space-time can be approximated as homogeneous on scales, averaging scales over 100 megaparsecs. And one should keep in mind that this is what the real universe looks like. So there are at least three possible ways in which our observations can lead to biased conclusions. One is, of course, the propagation of light through a system like that is not the same as the propagation of a null geodesic in a homogeneous background. The light will suffer deflections, so that's called gravitational lensing. And indeed, today there are many programs, observational programs, to map the gravitational lensing of distant objects in the microwave background. And what you want for that is, along a line of sight, what is the level of structure, because each one is going to cause a little bit of deflection, and the deflections all add up to a net shear of the images on the sky, which is what you measure. Also, you can see that if I look along this direction, it may not be the same as looking along this direction. There are mainly voids in this direction, and matter always will, gravity responds to the local matter distribution. As Patrick mentioned, you have the equivalence of Birkhoff's theorem in general relativity. You don't have to really care about what's outside, only what is inside the sphere. And therefore, if there is a local underdensity, the expansion rate there will be faster than when there is a local overdensity. So the expansion rate is not constant everywhere. So we talk about the Hubble constant, which is supposed to be constant in space, only vary in time. But in reality, the expansion rate, the Hubble parameter, must vary in space as well, right? We don't normally talk about it because in a Gaussian random field, the expectation is that the fluctuations of the Hubble parameter are quite small, no more than 1 or 2%. But that's only in that model universe. We have to ask ourselves what it is in this real universe, which does not necessarily correspond to the model universe. And the third question is actually got a name. We call it cosmic variance. This is the issue of whether all observers are the same. So similarly, surely it must make a difference whether I'm sitting in the middle of that or in the middle of this as to what I see around my neighborhood, right? Yes?
So do you mean that Hubble expansion is not isotropic?
Well, that is something for us to experimentally determine. Okay, I'm saying that if I gave you the distribution of matter to be like that, right? General relativity tells us that the expansion rate at any point responds to the local amount of matter. Does it look to you like it would be the same in every direction from here? Now, you have not heard of there are no large anisotropies in the Hubble expansion rate, but there are possible variations. So the only study I know of this that was done was actually by a Canadian relativist and his student, and they looked at the 65 measurements of the Hubble parameter using 65 galaxies in the so-called Hubble Key project. Okay, the Hubble Key project, which is supposed to have measured our local Hubble parameter with great precision, right? So when you map that on the sky, they found that there were variations of the order of 5-6% between neighboring directions. And then they added, and these were all within 30 megaparsecs. So the Hubble Key project actually measured 30 megaparsecs is about 100 million light years. So they only measured the Hubble parameter in that region. Okay. The question I'm asking is somewhat broader, right? If I were to be able to measure the Hubble expansion by some new tool which goes over a larger region, then would I actually get the same value? The answer to this question, as far as I know, is not known, because nobody has done it, right? The tools were not there. Also, most of the surveys that I showed you, the Sloan Digital Sky Survey, it is not isotropic on the sky. There are only little patches on the sky which have been mapped, because the field of view of a big telescope is tiny, right? So the question arises, when I say all directions are equivalent, there might be observer bias. So supposing I'm an astronomer, I want to make observations, I would naturally pick out directions in the sky where there is less dust or less intervening galaxies or whatever, because I want to get a nice clean line of sight. But I can see from here that that might mean that I'm more biased towards directions which have just got voids. And voids expand at a different rate than where there is matter, right? So the answer that I get might depend on the direction, right? Now, whether or not there are really such selective biases in the observations, I do not know. That is for us to find out. You see, these are questions that are not normally raised. But when you look into it, you realize that actually this Hubble Key project, which says Hubble parameter is 72 plus minus 7, does that plus minus 7 actually include the possibility of variations simply because of the sampling that you are doing of the sky? You can look into it and tell me the answer, because this is something that, when you ask professional astronomers, most of them haven't even thought about this, because psychologically you call it the Hubble constant, so you sort of think that it should be something which is fixed. So I just wanted to say, all observers the same, that actually does have a name called cosmic variance, because it is now recognized in the context of studies of the cosmic microwave background, that whereas the microwave background is isotropic on average, of course you break up the anisotropy, you expand it in special harmonics, and the large scale structure and the small scale structure are quite different. The small scale structure is very different all over the sky. So for example, if I try to measure the 2-point angular correlation of this room, so the difference between that point and that point and that point and that point is almost the same. It doesn't matter. This is a statistical, almost like a Gaussian random field. But if you ask me what is the quadrupole of this room, or the dipole or the octupole, it does matter where I'm standing. Whether I'm standing at a point of symmetry at the center of the room or at one edge, I'll see a different quadrupole, right? So this goes by the name of cosmic variance. Our particular position in this random Gaussian density field that the universe is supposed to have evolved from will determine what I see in terms of large-scale anisotropies. So these are questions that are raised when you actually look at a real map of galaxies. But this is the last pretty picture I'm going to show you, because from now on we'll get into the standard picture of cosmology, which says we ignore all this and we assume that on large scales the universe is homogeneous. So okay. So let's start with something that you all know, special relativity. And you know that the essence of special relativity is that we can construct something called the interval between two space-time events, and that is invariant for all inertial observers, right? And the interval is some metric. This Gij, this is the metric that we have to construct in order to be able to measure these things. So it's all about measuring intervals. Now, this is a 4x4 matrix, so there are 4 times 4, 16 elements, but of course it is symmetric, so there are only 10 independent numbers, right? So you can reflect it above the diagonal, it's the same. Now, the Minkowski metric, which describes special relativity, the signature, I'll adopt this signature, right? Time, space, space, space. And this has this simple form that you all know, which says that neither time nor the space interval is by itself invariant, but this difference is invariant, and this is the interval that defines special relativity, along with the fact that, of course, I have not literally explicitly written C, but that's what's the conversion factor between space and time. Right? So this is something we know how to do to map intervals in space-time, and this is, of course, the basis of almost all our experience. And quantum field theory is also formulated in flat space-time, so this is all part and parcel of special relativity plus quantum mechanics is field theory. Now, what happens when you go to larger scales? Well, immediately a problem arises that this interval is invariant under Lorentz transformation, so this is actually equivalent to the local inertial coordinates of Newtonian mechanics, right, or Galilean mechanics. But in general relativity, this metric is not something that exists independent of matter. It is actually determined by the distribution of matter. This was Einstein's great insight, as you know, behind the construction of general relativity. But this raises a problem, which maybe it's not a problem for most of us, but it was a problem for Einstein, which is that if I take away all matter, then I should have the Minkowski metric as a solution, right? So I should then be able to define an inertial frame in the absence of all matter, and this is contrary to something called Mach's principle, which I'll tell you about in a second, right? So Ernest Mach was, he thought a lot about the nature of motion, okay, and he asked the question, how are inertial frames actually determined with reference to what? And his argument was that it is determined relative to the distant stars in the universe. They define the frame with respect to which we define what's an inertial frame. And you need matter to do that, so you can't actually define an inertial frame in the absence of all matter. And yet, if I take away all matter, then the metric is that of Minkowski metric, which is in fact defining an inertial frame without respect to matter. Now, this is not really part of my lecture course, but I just thought I'd tell you this, because these days I know all of you will immediately look up Wikipedia to see what it is about. And this is simply to give you a little more interest in looking up a particular entry on Wikipedia, which is called Newton's rotating bucket experiment. Look at that, because these are actually still outstanding issues in our understanding, philosophical, if you will, understanding of space-time. So Newton's rotating bucket experiment, this is in his own words from the Principia Mathematica, is that if you take a bucket of water suspended by a rope from the ceiling, and then you twist the rope and then let go, the rope will unwind and the bucket will start spinning, right? And what will happen? In the spinning bucket, the water surface, as he says, will recede little by little and ascend to the sides, forming itself into a concave figure. He did the experiment himself, right? And the swifter the motion, the higher the water will arise, right? Now, so if you look at that thing, you can immediately tell that the bucket is rotating, right? That's what's causing this centripetal acceleration that is causing the water to rise up. What is the bucket rotating relative to, right? What is the frame that defines the fact that the bucket is definitely a non-inertial frame? It is causing a non-inertial force, namely the centripetal force on the water molecules, that are causing them to take an obvious curved shape. If I just take a film of that, one picture of that curved bucket, I can immediately say that must be a rotating bucket. I don't need a time-lapse photography, right? And this is quite a non-trivial question. Lots of people sort of remarked on this. So Leibniz agreed that there is a difference between so-called absolute true motion, which is something we just say in Newtonian mechanics without actually defining. There is a kind of a tautology there. There is a circularity between the definition of the third law and the definition of an inertial frame. And Mach himself says that Newton's experiment with the rotating bucket just teaches that this motion is relative to the mass of the Earth and other celestial bodies, right? So he is basically arguing that this reference frame with respect to which the bucket's frame is clearly non-inertial is in fact the reference frame defined by the distribution of matter in the universe. And in fact, he argued that if the bucket, this is quite an interesting remark, if the bucket walls become more and more massive, who knows how the thing would actually look, okay? So Einstein was very sort of taken by this. I'm not going to dwell on this. I've just said this to pique your interest if you are interested in the underlying foundations of mechanics. But Einstein basically wanted to formulate a theory of the universe, of cosmology, without violating Mach's principle. Okay, so there are only two ways out. One of them he could not adopt. So he first said, let's add some boundary conditions which make Gij become pathological, right, in some way, when you are very far from all matter. In other words, when there is no matters left, it's no space, in the intervening space, then Gij should not become the eta Ij of special relativity, which would violate Mach's principle. It becomes something weird, right? But de Sitter, who was a cosmologist in Leiden, with whom Einstein corresponded, wrote to him and said, that's nonsense. Even look at the light of a distant star, it is crossing empty space to come to us. You can't say that there is something funny going to happen in the empty space. Then, how is it that the stars look as they are? Nothing appears to be going on. So Einstein agreed that didn't work, right? The second option was that, let's say the distribution is homogeneous and you curve round space-time on itself so that you can't actually get away arbitrarily far from all matter, right? And this is the analog that people normally use to describe this. So you think of it as just like a balloon is a two-dimensional surface emptied in a three-dimensional space. You can think of our space-time, or space rather, as a three-dimensional surface in some four-dimensional space. The fourth dimension is a completely fiducial, notional dimension. It does not necessarily exist. It's just an embedding that we are talking about now. So you are going from S2, the surface of sphere, to an S3, which is then embedded in some four-dimensional space. The advantage of this is that you have a finite spatial volume but no boundaries, and the metric is not singular anywhere, right? It's a sphere. The poles apparently look singular, but that's just a coordinate singularity. There's no real singularity. So this is the process by which you came to formulate the metric, and what I'll take you through is the derivation of the Robertson-Walker metric, as it is called, just to show you that it is simply the embedding of a three-dimensional sphere in four-dimensional space. So Einstein's world model had homogeneity, and this is what, in fact, Hubble observed in 1926, and that is actually called Hubble's law, not what people normally call Hubble's law. So this was published in the Proceedings National Academy of Sciences, and I've already shown you in the first lecture the actual data on the magnitude distribution of galaxies, which is quite consistent with that, right? In fact, Einstein didn't even know about that. He just assumed that it was the case. And it incorporates Milner's principle, which is that, as I said, that our position is nothing special about it. It's kind of an extension of the Copernican idea. And you can technically define a so-called synchronous gate. So you imagine a whole infinite number of observers, each carrying clocks and rods and what have you, who can exchange information with the neighbor, and they can cover suitably, or you can foliate space-time into almost, in our case, it will be almost flat. The time-like directions, time-like spaces can be nearly flat because the perturbations are generally going to be small, and these observers can coordinate and synchronize their clocks with each other, and thereby, for all practical purposes, define our coordinate system, right? So this is the standard model that we are actually using today, right?
So excuse me?
Yeah.
Are these observers making shells of constant time to foliate the universe?
No, these observers can be, of course, in principle, the observers can be anybody you want. The point I'm making is that in this universe, we are not assuming that there is any funny things like black holes or whatever, right?
Fine. So what I'm asking
yeah.
is, are they making hypersurfaces of...
So, yes, you can make constant time hypersurfaces in this universe, but there will be always a little difference between that surface of exactly constant time So when it comes to discussing perturbations on this space-time, then you have to define a gauge and be careful about what you're doing. But we are not going to get into that here, right?
Sir,
Yes?
can we explain that synchronous gauge concept?
So this is just a matter of defining what. So time is a very vexed concept in general relativity, okay? In general. For example, in flat space-time, we can have local. So energy, which is, let me put it like this. The notion of energy is well defined in flat space-time. In curved space-time, it is not well defined, okay? And energy and time are very closely related. So think about it like that, right? So of course, locally everything is fine. Everything is flat, Minkowski space-time, because that's the way you are constructing it. But globally, you will find that the metric that we are considering, it does not become asymptotically like Minkowski space-time at all. It never becomes Minkowski space-time at large distances. So this is quite different from what you might have encountered as, say, Schwarzschild space-time. Asymptotically, it is flat. It's Minkowski space-time. This is not going to be the case here. So we have to worry about what time observers record. In this case, you synchronize with your neighbor. That's the way. So it's only an infinitesimal transformation that you make. So I don't know why the picture is not coming out well. This is meant to be a sphere. So sorry, let me just see if there's something about this projector. So what I've tried to plot there is a, oh sorry about that. Okay, imagine a sphere here, and these are curvilinear coordinates. So there is r, theta, and phi, right? You can imagine that. And on this sphere, also imagine a circle, which is like a circle of latitude, right? So this circle of latitude has a radius little r, and the sphere has a radius capital R. Okay, so now I'm considering a circle, okay, which is one-dimensional on a two-dimensional surface, which is a sphere, and trying to illustrate the difference between the coordinates of the one dimension to the two, because that analogy will take forward in going from 2 to 3. So the set of points that defines this big sphere, I mean, this is, in any case, the picture is only an approximation because I can't really show 4 dimensions on this plane. The set of points that defines a sphere S3, which is with radius r, is just x squared plus y squared plus z squared plus, let me call the 4th dimension w. Okay, so you agree that that is the equation of a sphere, and I'm saying it's a sphere in a space with 4 spatial dimensions, right? And the little r is in this case it's a circle. This is of course a sphere with 3 dimensions, x squared plus y squared plus z squared. This is just like our Earth, right? So if I wanted to, what I want to do is to embed something which looks like a ball, our Earth, into a 4-dimensional space, which is quantified as a sphere whose points all obey this constraint, right? So the line element dl squared will be dx squared plus dy squared plus dz squared plus dw squared, right? But I can substitute now this dw squared in terms of little r squared dr squared by capital R squared minus r squared by just using these 2 identities. It's trivial. If you can work it out, right? But you can start seeing something familiar emerging here, right? So I can write the line element. Now I can transfer to curvilinear coordinates in terms of theta and phi. So you know that I can write dx squared plus dy squared plus dz squared as instead dr squared plus r squared into d theta squared plus tan squared theta d phi squared. This is just the line element in curvilinear coordinates, r theta phi, where I repeat, r is the radial coordinate, theta is the polar angle, and phi is the azimuth. You know all this. So I can then rewrite this thing in terms of this suggestive looking expression. So theta and phi normally will not be concerned about, because if you have isotropy then all directions are equivalent, so you're not really going to be worried too much about that part. But I can combine this plus this into writing dr squared times divided by 1 minus little r squared by capital R squared. Okay. So now I'm beginning to get a line element which in if I write it in terms of polar coordinates, looks like that, right? It looks superficially like a Minkowski metric, but with different, instead of this part, this thing is chi is the polar angle of the hypersphere. Okay. So already this metric, which is the embedding of a three-dimensional sphere in four spatial dimensions, has very interesting properties. Because imagine you're sitting at the top of this sphere that you can't see, and maybe it's just as well you can't see it because you can't really draw it properly on a flat sheet of paper. But you can imagine that if there is a radius that defines the, actually the slide should be on a web page, so you can look this up there. So little r is the radius of the line of latitude that is running around, right? And when little r is small compared to big R, which is the internal radius of this big sphere, then space looks flat. So just like when you're looking around, it looks flat around me. But if I start looking on a length scale which is comparable to the size of the Earth, then I'll start seeing its curvature. Right? In practice, even if I look about 10, 15, 20 kilometers, I start seeing a horizon, and I know that I'm not really on a flat Earth. In fact, when little r becomes of order capital R, then you can see that the angular size, which is capital D, supposing I have a rod D and it keeps going away from me, then it actually reaches a minimum when chi is pi by 2. So when I increase this angle, right, this polar angle of the hypersphere, when I reach the equator, it actually becomes a minimum, which means it has got very far from me. But after that, if I keep going, then it will start diverging again, and it will fill the whole sky when chi is pi. So, if you have ever wondered about the following question, people keep telling us that the universe started in a big bang, in a compact, small thing, right? But when you look out at the sky and you see further away, things are getting smaller and smaller, right? As they go further away. But the universe is getting bigger and bigger. And then you ask yourself, how is it possible that if I look far out enough, the universe was actually, very, very compact? I don't see that when I look at the sky. Well, the thing is that if you look far enough, you will see that. And the reason why it seems to fill your whole sky is because imagine you're sitting on the top of a ball, on a sphere. And light can only come to you along the sphere. It cannot come through space, but only it is constrained to come to you along the surface of the sphere. So indeed, as you look further and further away, you start seeing more and more of the sphere, but once you get past the equator, it starts shrinking. And then when you get to the South Pole, if I have a source of light there, then the light will come to me from all directions, and it will fill my whole sky. So the Big Bang, if you like, is the antipodal point of this hypersphere, where we are sitting at some point, right? And that point is arbitrarily chosen because all points are equivalent on a sphere. Right? And now if this ball scale is changing with time, I will see exactly the phenomenon of redshift, because the photon wavelengths will be stretched out. And I will infer from that the universe is expanding. Actually, that's not a very good way to put it. You should really, I'll come to it in a minute, you should really say that, the scale of my space-time is changing, right? Otherwise, you could ask, what is the universe expanding into? And there is nothing, except the metric is the only thing that we have to make measurements with. So we should only talk in terms of the metric. The universe is not expanding. The metric of space-time is changing with time. That's what we observe. And this explains then what the Big Bang would be. It is the antipodal point of this expanding ball, if you want to have an analogy, right? These are all analogies because mathematically I can always do a transformation in which I take out that expansion, everything looks static, and then I can define something called conformal time, which takes into account the scale factor, and it will look like a Minkowski metric. So, but the phenomena is still the same. We should only talk in terms of observables. What can be experimentally or observationally determined. The interpretation of the rest of the things is just a waste of time because that's all matter of language. All we have is this equation that defines what we can measure. This is something you can measure, right? So again, the parallax, if you look at the parallax, it goes as cotangent of this polar angle, And you can easily see for yourself if you take the expression from here that it vanishes at 90 degrees. So there are all kinds of interesting visual effects possible in curved space which do not happen in the flat space that we are normally used to, where parallel lines never touch each other, cross each other, and so on. So the spaces that we are talking about in cosmology are so-called maximally symmetric spaces. They have the maximum degree of symmetry possible. Okay, and that is the way. Why? Because that's the way Einstein assumed it to be when he first started doing this to construct a cosmology, and that is the basis of our standard model. Maybe one day we will get a bit more adventurous and go a bit beyond that to see what else is possible. So I want to interest you in looking along those directions. But the difference is precisely whether two parallel lines never meet or cross or diverge, right? So that is the difference between what we would call flat and positively curved and negatively curved, like the surface of a saddle. And the test experimentally would be to add up the angles of a triangle and to see if they're exactly 180 or more than 180 or less than 180, right? I mean, it's interesting that even Friedrich Gauss, the mathematician, he actually tried to measure the curvature of the Earth by measuring the interior angles of a triangle near Brandenburg. Of course, he didn't have the precision of the tools necessary to do this, but if you, in principle, you can do that. And actually, we have now done this test, in a sense, measuring the angles of a triangle with a standard ruler on the microwave background, and in fact, the angles of a triangle add up to pretty close to 180. So we have inferred that space, not space-time, but space is actually flat in the universe that we live in. But there is an interesting question. Again, I put in a slide about this to intrigue some of you, I hope, who might want to look into it further. We are looking at a space with very simple topology. It's simply connected, okay, in topological terms. But in principle, there are people, and I refer you to this nice review by Jean-Pierre Luminet, who wrote a nice detailed review about it with all the necessary background references, as to whether the universe might have a complex topology, because people who look at fundamental theories and string theory and so on, it is quite possible. I mean, they do have spaces with non-trivial topology, and whether or not this actually have survived into the present universe is a matter of speculation and debate. We have no observational reason to think so. But you can, in fact, consider the possibility that the universe does have non-trivial topology and ask what observables can we define in order to constrain that. And the largest scale observations we can make today are of the cosmic microwave background. And in fact, one possible observational consequence of space being multiply connected would be that you see multiple images of the same object, which you might know because it has got exactly the same spectrum, right? Repeated on the sky, and people have done already this test on the microwave background. And the bottom line today is that if there is a topology scale, it is at least as big as our present Hubble radius. So in other words, there are no interesting consequences, as far as we are concerned. We are not in an infinite hall of mirrors or something like that. We have not seen that. But there could be other more subtle aspects. So that is still something worth, I think, investigating further, right? It's a matter of trying to figure out what you could define as an observable. So far, it has just been the usual multiple expansion of the CMB temperature patterns. But there could be other things, right? In fact, it was suggested to explain a certain observational anomaly in the CMB, which is that the quadrupole and the octupole of the CMB appear to be aligned with each other rather than oriented in random directions. And that is something that you might expect if space does have non-trivial topology. So, okay, so we come to the expanding universe, which, as it says there, was initiated by Friedman, who was actually a Russian fluid mechanics, that was his specialty, and Lemaitre, who was a Belgian cleric, a priest. So, cosmology had some interesting beginnings, right? And what they said was that you have to consider the possibility that in this metric, the scale factor that we defined, which was for a, that was some static metric, it could have a time dependence, and we could absorb the entire time dependence into one scalar parameter, which is called the scale factor, which changes with time. If we do this, then the expansion is self-similar. A triangle will remain a triangle with exactly the same angles between them, right? So it's just that the scale of the triangle is increasing or decreasing, and correspondingly in the space that we inhabit, galaxies will seem to be going further away from each other. So this triangle defined by these galaxies just becomes a bigger triangle, right? And if you run it backward, it becomes a smaller triangle. This is reversible, right? But there is no shear, there is no distortion of the shape, right? Because there is only one scale factor, and that just depends on the time. It has no dependence on space. What we were discussing earlier is the possibility that actually there are irregularities here because of density fluctuations, but when you average over them, this is the picture you should get, right? So now that scale factor that we had defined earlier, we can write it in terms of this time-dependent part, right, and the usual curvilinear element that we already defined. And this is a spatially closed expanding universe. If you want to have an open expanding universe, I just need to change the curvature of space from positive to negative, and the simplest way to do that here is to change this polar angle to I times the polar angle, r to I times r naught. So basically the sine functions just become sine hyperbolic. That's all. So this is the fun with metrics. Once you define one, you can play all kinds of games with it and start constructing whole families of models or model cosmologies with different curvature and so on. But it's very trivial. I mean, the mathematics that I'm describing is totally very straightforward, right? I mean, and yet this is the basis of cosmology, so we have to pay attention to this, right? So when we do this thing and we get these hyperbolic functions, this is called the Robertson-Walker line element due to H.C. Robertson and Walker. This is the line element for maximally symmetric space-time, and you have encountered this before, written in this way where this object is actually got no dimensions. And what I've shown you is where this actually comes from. It is just the line element of an interval on four-dimensional space where the fourth dimension is a fiducial, imagined space dimension in which a three-dimensional space is embedded. That three-dimensional space can have either positive, negative, or zero curvature, and the radius of curvature of this space is described by some large number like this, what we have called here r naught, but it is being allowed to change with time. That time dependence is entirely absorbed into the scale factor. The rest of these are just curvilinear coordinates. As I said, this part will largely not matter because we are not going to usually deal with situations where there is any theta or phi dependence on the sky. The sky is isotropic. So it is just this part here, right? Which is not that different from the Minkowski metric except for this thing here, right? It's not just dt squared minus dr squared. It is dt squared minus dr squared times a squared by 1 minus kappa r squared. Right? But we can do a transformation called a transformation to conformal time that will even take that away and make it look like a Minkowski metric. So these are the three possible geometries of the universe. This is from, actually I took it from a Scientific American article by Martin Bucher and collaborators, where they kind of try to imagine how Escher would have drawn a grid which has got positive curvature or flat curvature or negative curvature, and you can see visually what space would look like if you actually manage to fill it with some geometrical grid. This is what it would look like. Of course, there is no geometrical grid or galaxies are not at regular intervals, but we can infer the geometry from, as I said, measuring structures on the cosmic microwave background. Okay, at this point I'll pause. Yeah. Yes. No, so the infinite, so I defined it as a compact space embedded in 4 dimensions, but of course I did not tell you what the radius of curvature of my space is. That could be infinite. I just take R to infinity. So in practice, the bit of the universe that you can see is the bit from which light has been allowed to reach us. Right? Sorry, what was the question? Yes, but I'm saying that it is part of the same family of solutions, right? So actually there is no mathematical distinction between, well, the mathematical distinction is that the curvature is of opposite sign, right? So I can have negatively curved, positively curved, or zero curvature. Now, zero curvature is the limit of positive curvature where I take R to infinity. So it is not, I mean, there's nothing funny about it. It's just a well-defined limit. Just like the Earth looks pretty flat to us, that is the flat limit of a curved sphere. And the Earth is flat. As far as I'm concerned, it's quite flat, especially in Delhi. Yeah.
The K factor
Huh.
in your expression. So you are just expressing R0 with the Nastby's relation, right?
Correct.
The other K factor can be
The K factor is, oh sorry, I should have mentioned that. So I'm scaling everything in terms of this R0. So K is just the sign of it now, right? So the actual degree of curvature, about the sign of the curvature, is it positive, negative, of 0, because I'm now measuring everything in units of R0 square.
it's a hand put in you.
Huh?
You put it by hand.
Yeah, I'm put it in by hand precisely to as a reminder of what is the sign. That's all. So K will be either +1, -1, or 0. It has no particular value other than that, because the actual magnitude of the curvature is contained in that R0, which has dimensions. I want to work with a dimensionless quantity for convenience, with a dimensionless scale factor. So actually, when again many textbooks muddle this up. Sometimes they have a scale factor with dimension, sometimes without. But for practical purposes, we are generally concerned with the propagation of light with null geodesics. Okay? So with j square equal to 0, and there it is convenient to have a dimensionless scale factor typically. So I mean, all these things are relative. We have to define what you are defining respect to. So far, I have no length scale in the problem at all. Dealing with maximally symmetric spacetime, no inherent length scale, right? No maximum or no minimum. So okay, so this is the evolution of these world models. So if it was a ball, it would become a larger ball, and actually, as you'll see, if there is enough matter, such a ball would recollapse back to a small ball and onto the initial singularity. A flat thing would asymptotically keep expanding. Okay, and if it is negatively curved, it would also keep expanding and in fact keep getting bigger and bigger. Right. So in all cases, I'm saying that we are only observing some little patch of this. So again, when these questions of how large, where is the edge, and so forth, we're only observing a little patch, the patch that is within our light travel time, right? As it happens, the universe, we know from other reasons, as Patrick mentioned, is of order, whatever, 14 billion years. So you know that 14 billion light years is the maximum we can see. So far, we have only been able to look up to the point directly where the microwave background decoupled. But actually, in principle, using, say, gravitational waves, we might be able to look beyond that, even when the universe became opaque. So actually, tomorrow I'm giving a public lecture where I'll discuss this. Where is the edge of the universe, especially in the dynamic universe that we think we live in? So now let us get more concrete. So the redshift is happening because this quantity, this object here, dt over a of t, and now I substitute from this metric that I had in the last slide. Okay, so I'm substituting for this thing here now, right? So I'm setting ds square equal to 0, and then that will give me that the dt over a of t is just dr over 1 minus kr square, right? And this is some constant, so that if I imagine a galaxy that emits light at some particular time t, and I observe it at time t0 is the present day, then the time interval will be dilated according to that formula, and that is what I am calling the redshift, because my spectrum, the dilation of time is equivalent to things being shifted towards the red. The wavelength is stretched out, right? So on this expanding space, a wavelength becomes longer and longer. So therefore, I can see that what I am calling the redshift, Z, is simply the ratio of the scale factor today to the scale factor when the light was emitted, and we usually define it as 1 plus Z. So because today, of course, the scale factor by definition is the scale factor, so there is no redshift. Whatever is the wavelength is defined as the laboratory wavelength today. So the redshift has actually got nothing to do with the Doppler effect or anything of the sort. It's simply the ratio of the scale factors. Of course, locally space-time is Minkowski, so you can always talk in terms of a Doppler effect. But you cannot really do it when z becomes large, because then you might say, I don't want the velocity of the galaxy to exceed the speed of light. And that would mean that all galaxies far from us are going at 0.99999999 of the speed of light. And that would then mean that such a universe is not homogeneous, because there is no distinction between a galaxy at 1000 megaparsecs and one at 2000. They're both going at the same velocity, which is very close to that of light. In practice, the scale factor can be stretched at any speed you want, because it is not unobservable. So there is no problem in interpreting redshift in this way. Redshift can be very high. Redshift can be 10 to the 12. I don't care. It just means that the universe was, at that time, characterized by a scale which is 10 to the 12 times smaller than it is today. Nothing wrong with that, right? Otherwise, the problem with this Doppler interpretation is that immediately you start thinking in terms of, oh, we'll start violating something. Nothing is being violated here. So this is literally what's happening to the light as it propagates to us from when the scale factor was smaller. It is just stretched out to a longer wave, and that is what is causing this redshift. And you can see literally from here that it is really just the ratio of the scale factors. This is as simple as it gets, okay? I'm talking about isotropic, homogeneous, maximally symmetric space-time. We don't have a difference between expansion one way and the other that would introduce a lot of complications. So this I've already mentioned. So the antipodal point of this hypersphere is the furthest we can look back in principle, right? Which is something of order of 14 billion years, right? But of course, this is a construction. So don't ask questions like, can't space be there, or can't there be some stuff outside it? Of course there can be, but this is what you have constructed. We can only talk meaningfully about what you have constructed, right? And as to, people ask, what is before the Big Bang? Well, in this model, there is nothing before the Big Bang. It's the antipodal point. It's like asking, as Hawking famously said, what's north of the North Pole? There's, by construction, there is nothing. Whether there is actually something, you can only ask that question if you formulate a bigger picture where it can be a sensible question. In this context, it is not a sensible question. And this is just a comment for, this most of you know, but maybe some of you are new to this. Of course, as Patrick also mentioned, everything is not expanding, because otherwise you would never know, right? Rulers are expanding at the same rate. So the statement is that anything which is bound by a non-gravitational force is not expanding. Atoms are not expanding. The solar system is not expanding. Galaxies are not expanding, because they are bound by whatever force that has overcome the large-scale stretching of space-time that is described here, which is a very, very slow process, right? So it's only the metric that is expanding its cosmic time on scales which are large enough that the average can be taken as a smooth continuum, okay? Which is typically on the scale of intergalactic space, not on any scale smaller than that. And there is, as I mentioned earlier, there is no restriction on this rate at all. And in fact, as Dennis Sharma always like to sort of emphasize to me, there is actually no expansion, because all I had to do is do an inverse transform where all the galaxies are at rest with respect to each other. You can just transform this scale-dependent transformation. You can just do a inverse transform and just take it away, right? So then, nothing is changing. So what is the expansion? So that is to address all the people who ask, what are we expanding into? So now we have to fill this space-time with matter, and classically, that is to say historically, the only kind of matter that was considered was called dust. This is just ordinary, what you would call non-relativistic particles, whose energy density is dominated by their mass. Their kinetic energy is negligible compared to their mass energy. And therefore, effectively, they have no pressure. Pressure, as you know, is kinetic energy for example, the pressure in this room is the kinetic energy of the gas particles. But the gas particles in this room, their mass energy is hugely bigger than their kinetic energy. So effectively, the gas in this room constitutes what is called dust in cosmology. And that will have an energy momentum tensor, which is, of course, diagonal, because I have not given this fluid any torsion or anisotropy, viscosity, anything funny like that. And it will therefore be subject to Poisson's equation. The only thing that I'm introducing, which is generally relativistic, is that the energy density is the total energy density, which is not just the mass, but also the kinetic energy, right? This is the kinetic energy. So what Einstein tells us is that all energy gravitates. Doesn't matter what kind of energy it is. Potential, kinetic, it all gravitates. So I have to add that 3p term, right? And in fact, the usual foliation that we have done of space-time is that basically galaxies move without intersecting each other. They don't collide. In fact, I showed you in the last lecture that galaxies do actually cannibalize each other, etc. That's complicated astrophysics. But for the simplicity of the mathematical model here, we are assuming particles that basically evolve without actually intersecting each other's geodesics.
So the G in this equation is a metric, or
This is this one.
the one on the left?
So that's the acceleration. Okay. So you can write the rate of change, the acceleration in terms of g.
Gravitational field.
Yeah.
Newtonian.
So this is Newton's constant. This is the total energy density. This is just the gradient of the force, if you like. So you still have the equivalent of Newton's iron sphere theorem or Birkhoff's theorem in this space-time. So if I just make a little hole, then all that matters is the matter within the hole for determining the motion of a test particle at the surface, right? And that would give us Einstein's field equations. So we are now simplifying Einstein's equations enormously, because in principle, I told you the Gij, there are 4 by 4 components. So you can write down a number, even if it is symmetric, there are still 10 equations. But because of this, I can just write down very simply by using this Tij, the Einstein equations, which normally would have many components, because we have these are the quantities that are constructed from the metric as follows, and this is the energy momentum tensor for which I'm adopting a simple diagonal form, right? This will simplify the 0 component, will give you so-called Friedmann's equation, and the 1 component will give you what some of us call the Raychaudhuri equation. So A dot by A, this is the so-called Hubble parameter, that is then determined just by the energy density, right? For pressureless matter, it is just the mass density, and the multiplier is just Newton's constant, and this K, see, it's K over A squared. So I have actually retained the information about how much the internal radius of curvature is, right? So K is just telling me the sign, but the 1 by A squared is going to tell me just how big or small that space is, right? So as time goes on, A will increase, so the curvature is decreasing all the time. And this A double dot is proportional. If it was in normal physics, you would just have had 4 pi 0 by 3, but now I have to add this 3p, because that is the total gravitating mass, including the kinetic energy. So the acceleration is expected to be negative, because of course gravity is attractive. So whatever set off the expansion, we don't know what set the expansion off, but it should be slowing down with time, according to this. In the expanding phase, in the contracting phase, of course, it is speeding up. Right? In fact, another thing I should point out here, when people sort of look at this equation, it's kind of clear that the expansion rate is proportional to the energy density. So for example, if I had more energy density, it looks like the expansion rate is faster. Okay? So if you think for a moment about it, that's a bit puzzling, because you would think that if I put more matter, then gravity should be stronger. So how come the expansion is faster? Should it not be slower, right? So your concern is not misplaced, but it is applied to the wrong epoch. When the universe is collapsing, indeed the expansion collapse rate is faster when there is more matter, but we are not looking at the universe in a collapsing phase, which is the context in which you look at all objects otherwise under gravity. They are usually falling. Okay? This is a very peculiar situation where it's like somebody has thrown a stone from under our window and it is just crossing my window, okay, on its upward trajectory, not on the downward trajectory. We rarely catch anything on an upward trajectory, but the universe is now on the upward trajectory, right? So that is why the expansion rate would actually be faster if there was more matter, because we are not asking the question who threw the stone. That is a different matter. So first let's start with Newtonian cosmology, because cosmology actually doesn't need, the simple cosmology that we do doesn't really need much in the way of GR at this level. It will only be relevant when we do perturbation theory. So if I consider this little sphere of radius L embedded in a homogeneous background, and this model is actually due to Macria and Mill, who I mentioned earlier, then it is clear that the acceleration of a test particle on the surface of a sphere of radius r is just the matter contained within that sphere divided by r square, that is the force at the surface. And what is this matter? That is 4/3 pi r cube times p plus 3 rho. So the sphere radius is L, so L cube, and then I have a 1 by L square, so the L square and the L cube cancel and leave me just L. Okay. And also, as this sphere, if this sphere expands or contracts in response to this dynamic, then it will, if the matter inside it has pressure, it will do work, right? And how much that is described by the law of thermodynamics, right? So rho dV plus P d rho will be minus P dV, right? This we know. So armed with this, we can do cosmology, because I can solve this equation to then integrate it once to then work out that the rate of change will be simply the logarithmic rate of change of the volume element, which is just 3 times the logarithmic rate of change of the scale, because the volume is just going as the cube of the scale, right? And this is the energy equation for an ideal fluid. So I can substitute back in this acceleration equation, and L double dot will now be, this is all simple maths, I will not take time over it, but it's all in the slide. So please work through this and satisfy yourself that the maths is correct, right? So I can write it in this form, which allows me to integrate it once. So L double dot I integrate once, I'll get L dot square, right? And that will be now proportional to G rho times L square plus some constant of integration. Okay. Now Einstein at this point, when armed with this, he actually made a mistake, because at that time there were no observations, as I've said a couple of times now. He assumed the universe to be isotropic and homogeneous, partly for aesthetic reasons. He considered space-time, the construction of the metric, in accordance with Mach's principle. No observations entered there, unless you count Newton's rotating bucket. But at this point, we did not even know that we are living in one galaxy out of 10 to the 11 others. So you have to place yourself in the historical context. As far as Einstein knew, the universe was static. Nobody had told him otherwise. Partly because he didn't read the astronomical literature, but anyway, he didn't know this. So he actually considered the possibility that in this equation here, if you have this rho plus 3p, if that thing vanishes, right, then you have a static solution, because then you have a unique radius for the universe, okay, which is determined by this equation here to be 1 over 8 pi 3 g rho, right? And this static solution that he constructed is actually unstable. And in fact, there is an interesting problem that can be said about this. All you have to do is to take this solution, perturb it slightly, and see what happens to the perturbations. The same way that you normally do perturbation theory for any classical system. You just introduce a little perturbation, in this case in the metric, in delta A, and see what the growth of the perturbation is, and you will find that they actually grow exponentially. So this space-time is unstable. You cannot have a static space-time under gravity, right? But in fact, Einstein recognized that this cosmological constant, as he put it, is in fact not something that he can actually get away with, because it is a consequence of the general coordinate invariance that actually underlies general relativity. So in fact, you have to admit of the possibility that any term can be added to that equation which I had in the previous slide, which is proportional to the metric, and this thing is called the cosmological constant, right? He chose a particular value for it in order to make the metric static, but that particular solution is unstable, and in general you should allow it to have any value whatsoever, because the underlying symmetry of the equation just demands that there be such a term. It does not specify its value at all, right? So subsequently, when people realized that matter was not necessarily described just as dust, that matter actually had to be described as a quantum field. So this was back in the 1930s. Zeldovich, Pauli, etc. started formulating the beginnings of quantum field theory, and they recognized that actually that the energy momentum tensor of a quantum field, which is not just described in terms of pressureless matter, but has more, it has an infinite set of oscillators after all, that also allowed of the possibility of what today in modern language you would call a super renormalizable term, which is the vacuum fluctuations of the field. That also acts like a cosmological constant. So they in fact moved this thing to the right hand side of the equation, but in principle there is both a geometrical part and a part that is coming from the energy momentum tensor, right? And those two add together to make up the effective cosmological constant in the equation. So one is coming from just the geometry, if you like, the freedom to add something to this left hand side as a consequence of general coordinate invariance and nothing else. And the other which is coming from the behavior of the actual quantum fields which make up the energy momentum tensor in the universe. The two are completely unrelated unless you put the whole thing on some special background where they might be related. But in general, they're totally unrelated. And yet, however they add together makes up the object that determines cosmological observables. And Einstein recognized that this was one way to discuss the matter further, but we'll come to that later.
Sir,
Yes?
that lambda Gi term.
Yes.
So is it like same way when we write a Lagrangian and add a total derivative in the Lagrangian? The equation of motion. So is it kind of the
No, so if it had turned out to be something like that, then we would have solved the cosmological constant problem. Unfortunately, it is not a constant of integration, nor is it a Lagrange multiplier, nor is it something that we can just do away with. That is actually an interesting idea, and a lot of people have tried to interpret it as such. Unfortunately, it doesn't work. We'll come back to that later, but that's a very good question. Right. So we now come to the dynamics of this FLRW universe. I'm slowly ramping up from Newtonian to the full object, because you have seen these equations before, but I think it's kind of interesting to see historically how they grew up, right? So now you have the second equation for the acceleration. As I said, that for if you have rho plus 3p, and this is the actual curvature. So here I'm now going to refer to the split the energy density and the pressure into stuff that refers to the background and the stuff that is the cosmological constant, which is separate. Okay. So background just means matter and radiation, whatever it is in the background. Of course, the matter in the background in principle also contains a cosmological constant in terms of the 0-point fluctuations, but traditionally that is absorbed within lambda. It's exactly the same object. So the lambda that we write down here is the sum of the geometry plus the field fluctuations. And then we have the conservation of energy momentum, which of course is absolutely fine when you're looking at a small volume. It's expanding. We ask what is the change in the total energy content as a consequence of that, and that would simply be given by the dilution of the volume. The volume goes as a cube, so you have a minus 3 a dot by a. That's all there is to it. Right? So it doesn't matter that total energy is not conserved in general relativity. You don't have to worry about that here. Now, if we integrate it, then we get this Hubble equation, which we have already encountered. But now we have a second term, which is the third term, which is cosmological. So there is matter, curvature, and cosmological constant. And the signature plus or minus, now I've taken out the k. You asked about that earlier. I can write down k here, or I can just say it's plus or minus according to if it's open or closed. Dimensionally, what matters is the actual radius of curvature of the internal space. Right? So this equation has two interesting solutions. The first one was due to Einstein and de Sitter, and they considered the case where you have just dust, so no pressure, just energy density, and no cosmological constant for whatever reason. Right? Actually, you have to justify why that is so, why lambda is so. Nobody has a justification, but this is the limiting case. And in fact, it is actually a pretty good limiting case, not for the universe today, but for the universe at early times, when the cosmological constant would have been negligible compared to the energy density of matter or radiation. In this case, I can integrate this trivially, right? A goes as t to the 2/3, the time scale t is 2/3 of the Hubble parameter inverse, and it is actually related directly to the energy density. So you can derive all that from here. This is called the Einstein de Sitter universe. It's a critical density, as I'll define shortly, universe which is expanding at t to the 2/3. The de Sitter universe had no matter in it at all, no pressure, no energy density, just a cosmological constant, right? So you can see from here, if a dot by a square equals lambda, then a goes as e to the square root of lambda, right, because of the square there. And if you put in the factor of 3, so that is square root of lambda over 3, and so it goes as e to the ht, where this h, the expansion rate, is square root of lambda by 3. And de Sitter actually proposed this as an interesting counterexample to this idea of Mach's principle determining everything, because this is a universe which has got no matter in it. It's just got a cosmological constant, right? And it clearly therefore violates Mach's principle. So he had motion without matter as opposed to Einstein's static universe, which was matter without motion. So these people those days, there was actually quite a small group of people who were in fact constructing all these cosmological models, and they in fact communicated a lot with each other. They wrote letters to each other, which make for fascinating reading. Yeah.
But once you postulate that this cosmological constant mimics the dark energy,
Yes.
then there's nothing against the Mach's principle.
So that came later, right? At this point, there's no concept of dark energy.
This is just a mathematical solution to an equation which is a dot by a square equals a constant. I have not called it anything.
No, my question is once you accept that, once you postulate that.
You are asking the question, is Mach's principle consistent with dark energy?
Yes, once we accept that this cosmological constant is mimicking the dark energy, then we can have it.
No, here the idea is that, as I said, motion without matter. Imagine two test particles in de Sitter universe. Test particle, very negligible mass. There is no, it's empty. Yet the distance between the two test particles
is exponentially changing.
Grow, although there is no matter. So it is against Mach's principle. Then Mach would say that all motion, everything is with respect to matter.
Yeah.
That's what.
Is a trivial example. In fact, one can give more arguments against Mach's principle, but I will not. Actually, it's the only example I know of a fundamental theory in physics being influenced by some philosophical idea, right? Fortunately, we don't usually do that, but this was one case. Mach also, by the way, didn't believe in the reality of atoms. So you can see why I'm a bit biased against him. But let me give you an interesting historical anecdote, which I think is quite amusing. De Sitter actually gave a third solution, which looked like this. Okay, he gave a metric which looks apparently static. Okay, so this part you have seen before. So now he has, this part you have seen before. Now in multiplying the dt square, he has got the same factor that you have in the denominator here. Okay, you've seen this before, right? Let's forget this part. Now this space is very interesting because consider a clock at rest in this universe, in this space, right? So at some particular point, that's the origin of coordinate system. The interval is 0. So what is the time-like interval? The time-like interval now, the interval is just dt squared 1 minus r squared by capital R squared, right? Now this is very interesting. As r, so r, capital R is the internal curvature, little r is the spatial distance. As r is increasing, this thing is decreasing, right? So the time interval is getting shorter and shorter, right? So this is exactly what redshift is, except that this redshift, which is again defined in terms of the ratio of the wavelength at emission to that at observed, right, usual way. So I can expand square root of 1 minus little r squared by capital R squared. When this is a small number, I can Taylor expand it, right? And the first term in the Taylor expansion, the 1 will cancel. The first term in the Taylor expansion that remains is little r squared by capital R squared, half of that. Okay. 1 minus r, little r squared by capital R squared to the half, square root, right? So it looks like the redshift is going as the square of the distance. Okay. So this was called the de Sitter effect. People expected, observers expected that the redshift would actually go as the square of the distance. And you have never heard of this, but this was a little episode in the history of cosmology that is airbrushed over, because a lot of famous observers, Stromberg, Lundmark, Silverstein, including Hubble, were taken in by this, and they tried to fit their data to redshift going proportional to the square of the distance, and they found it agreed, right? But in fact, de Sitter realized that what he had written down was actually the de Sitter metric. It is actually the de Sitter metric written in a funny way. And it is still an isotropic homogeneous space-time, and the redshift distance relationship has to be linear in any space that is homogeneous, okay? Because otherwise the triangle will not remain a triangle. So you cannot have this redshift doing anything other than proportional to little r for small. It cannot go as r square, because that will distort, okay? It will not keep the triangle shape preserved. So Hubble actually fitted his data to a quadratic relationship. In the famous paper that is normally ascribed to the discovery of the Hubble expansion and the Hubble law, he never actually mentions that it is supposed to be, the redshift is proportional to distance. He simply plots the data, and he says that there's a footnote where he says that he has tried to look for the de Sitter effect earlier, but in that paper, actually in a letter he wrote to de Sitter, he said, the interpretation we feel should be left to you and the very few others who are competent to discuss the matter with authority. In other words, he was burned once. He didn't want to goof again. And he said, we measure the redshift observationally, it's a well-defined quantity, and he measures the distances observationally using C-field variables and so on. The interpretation should be left to the theorists, right? So I'm reminded of this when one bad supernova observation immediately causes people to assume that the equation of state of dark energy is more negative than -1, which then starts violating unitarity and other things. That they should pay heed to Hubble's words, right? Be very careful, because once you construct a mathematical model, you might get all kinds of answers. If the measurement is not right, then you can get all kinds of unphysical answers. So here is a garden of cosmological model showing the scale factor versus time. And actually, as you see, at late time, so this is time, and the scale factor starts, in all cases, growing exponentially. Why is that? Because there was matter, curvature, and lambda. Matter is getting diluted with the expansion, so its effect is decreasing. Curvature is also getting diluted as 1 by a square. Matter is going as 1 by a cube. But lambda is not changing with a at all, so it will always come to dominate. And once it comes to dominate, by construction, the expansion rate should start going exponentially. So all these model universes are all dominated. So you have, this is the Lemaitre universe, which actually has a coasting phase. So lambda comes to take over at some point, and then people even found at one point evidence of a coasting universe. This was a long time ago, from the distribution of quasars. That has been discounted. So we are now obsessed with this idea that we are now in an exponentially expanding phase. But there is, of course, one universe that doesn't do that. That is this Einstein de Sitter universe, which is asymptotically going, coinciding with the x-axis. And this, in fact, is a perfect description of the universe at the time of CMB decoupling, because at that time, in this model construction, the only thing that was important was the matter density. Curvature was unimportant, lambda was unimportant, matter dominated, and it was the critical density by definition, because as you go earlier back, you go closer and closer to critical density. In fact, that is one of the puzzles of cosmology, why it is so close to the critical density. For practical purposes, omega was 1. So we know exactly what the geometry of the universe was at the time of CMB decoupling. There's a discussion going on about what is its state today, but this is what the model universes are constructed to do. Do not confuse the model universe with the real universe. We have to still ask ourselves what is the real universe. So here are a few remarks. Sorry, I've already gone on for, okay, I'll take 10-15 minutes. So we started 5 minutes late, right? So I'll go 5 minutes. So this is an important remark, that you can't actually reduce the Robertson-Walker metric to Minkowski metric even at r of infinity, because I can transform to a coordinate called conformal time. I can absorb the scale factor in the definition of time, and then it will look like a Minkowski metric superficially, but it is not, because it is compressing the time interval as a goes to, starting from minus infinity to 1 today, or depending on how you define it, that factor will be dilated very significantly. So whereas this is very useful, conformal time is very useful for thinking of space-time events in the context of Penrose diagrams and so on, you have to be very careful when you play with that stuff, right? But you can see that it actually, this part looks like a Minkowski metric. As I said before, we are typically ignoring the angular part, and this part will be unimportant as you go to early universe. So the other question you can ask is, these are all symmetric, maximally symmetric. What about less symmetric metrics? So for example, we could consider a metric that is isotropic but not homogeneous, or more generally both anisotropic and inhomogeneous. The problem basically is that the mathematics becomes very complicated, because there are very few exact solutions known of Einstein's equations. So we try not to go there unless you have to. One that has been considered, in fact it was proposed by Lemaitre himself and Tolman and Bondi just a year after the Friedman-Robertson-Walker metric, and they considered an universe that is inhomogeneous but isotropic. So what you do here is that you allow for an arbitrary function of r to multiply the radial part of the equation. Okay, angular part remains the same. This is the part that is reflecting isotropy. This is the part that is the radial part, and you characterize it by think of it as a general function of r, which characterizes the variation of the scale factor. So the scale factor in this universe does not just change with time; it also changes with space. Okay, but radially, it's the same in every direction. Now we'll see later that this, although this is now apparently in violation of the so-called Copernican principle, we have to be exactly at the center of this universe in which we are defining a radial function away from us. So, we are in a special position, no question about that, and that people don't like. But actually, this extra degree of freedom can completely change the interpretation of observations. Now, people don't like putting ourselves at the center of the universe, but the truth is that we are at the center of the universe insofar as I've emphasized, we can only make observations from our point in the universe. So by definition, there is something very special about where we are, because we can't go somewhere else and make observations. So I think that some of these objections to considering a metric in which we are at a special point are somewhat disingenuous, because they don't recognize the observational reality that we are constrained to only make observations from where we are.
But I think their point would be that were you to go somewhere else, you would see the same thing. That's the point of the...
Yeah, but the whole point is we can't go anywhere else, so we don't know what they would see.
We're constructing models for generic use, right, for the universe. So
Yes, but this is the only universe we know, and this is the only thing we see. So how can we be, I agree, that's a noble idea that, that whatever we see, whatever model we construct should be of general applicability, right? But the fact is that we live where we do, right? I might try to construct a model of the political system based on being in Delhi. It may not necessarily apply elsewhere in the universe, and I would be misguided in trying to do so. Okay. But yes, you are right about that. So, okay, so now this will not take very much time. It's all in the slide, so I'll go a little bit quickly through it because I want to take you to the, the boundary of the subject today. So basically, the Robertson-Walker metric can now allow us to define observables. So you can expand that in a Taylor series, and the first derivative we have already encountered, that's called the Hubble expansion rate. The second derivative is defined in this peculiar way with a minus sign, because it was widely expected to be a negative number, a deceleration. So you define it as a negative sign so that what you measure Q0 should be positive. That is what was expected, right? And that is how that is defined. And you invert this to obtain the redshift as a function of these quantities, H0 and Q0, which is just the inversion of the Taylor expansion here. And people then, you can also define the coordinate distance, which is just the distance traveled along this null geodesic. So now that you have the metric, you can compute all these things very, very straightforwardly. They just involve very simple integrals. You can actually do them right with pen and pencil paper right here. Okay, and the Hubble law that people often talk about, which was not Hubble's law at all, is that this H0 times D, this is going proportional to Z, Actually, it's a Taylor expansion. The proportionality to Z is just the first term of the Taylor expansion. So when Z becomes large, it is no longer linear. There are quadratic corrections to it, right? So what we call the luminosity distance, which we'll come across shortly in discussing the Hubble diagram of supernovae, is defined as so. Okay, so that's just the scale factor squared times this coordinate distance, Re squared times 1 plus Z squared. So this is essentially saying that in flat space, light will spread out as 1 by 4 pi r square. In curved space, it is still spreading out as this luminosity distance square if I define the luminosity distance appropriately, taking care of this scale factor. That's all. This is just so that we make a contact with our usual intuition about flat space. So the absolute luminosity of a source is, say, L. Its apparent luminosity will be just L divided by this sphere that is spreading out from it. And now, instead of just 4 pi r squared, I have 4 pi a square re square 1 plus z squared as just defined. And since this a is determined by the Friedmann-Lemaitre equations, we can derive from this the so-called matic relation, which basically connects the Hubble parameter and the Q0 parameter to actual observables, right? So using this, we can in fact determine from data what H0 and Q0 are, and to do that, we have to, of course, measure the luminosity of these objects. So the intrinsic luminosity is related to the apparent luminosity. So intrinsic is L, and little is the apparent luminosity, which is here. The two are related through this relationship, which is then sensitive to the deceleration parameter and the Hubble parameter, right? So people often talk about these things in terms of the fractions of the energy density in matter and cosmological constant omega matter, omega lambda, etc. None of that is actually necessary, because what we are really doing is entirely kinematic. The only quantities that you actually measure on the sky are the expansion rate and the rate of change of the expansion. So we can always interpret that in terms of dynamical variables, which I'll do next. But observation program can be entirely just a matter of measuring acceleration and velocity. Okay, we don't need to interpret them. The two are connected as so. So this gives me the magnitude redshift relation. So if I take that minus 2.5 log of L by N naught on both sides, I get the magnitude in terms of the deceleration parameter. So this expansion is okay for small redshifts. For higher redshifts, you have to actually calculate the integral, which is straightforward. And then if I rewrite Friedmann's equation in terms of not the energy density rho, but rather rho divided by a critical density, right, which is 3h squared by 8 pi g, then I can write it in terms of the fraction of the critical density in terms of matter, in terms of lambda, and in terms of curvature, if I had to add curvature to it. And the definitions of omega matter and omega lambda are here. Okay? So this is normally how cosmology is done in the present day up to redshift of order 1. And from this you can read off that Q0 is omega matter by 2 minus omega lambda. So normally we are not considering, if you don't have this, then Q0 is always positive, the universe is decelerating. But in principle, if this term overcomes that term, or if there are other terms that you have left out which can overcome that term, then Q0 will look positive. Okay? Remember that we wrote a very, very simplified equation with just 3 terms for a maximally symmetric space-time. If we did not write down the full equation, if there were other terms that we neglected, they would also actually enter. And then the simple omega matter, omega lambda universe would no longer be the full description of the story. So when we start getting inferences from that model which are strange, then we should actually go back and ask, did we leave out any terms that should have been added to this equation? One such term is called back reaction. I will not discuss it in this lecture, but I'm actually giving a talk about it at Jamia on Thursday. So this is the program that Sandage, who was a student of Hubble, embarked on, measurement of H0 and Q0, okay, in the evaluative cosmology. But this program was unsuccessful for a good reason. The reason was that these cosmological measures, like for example the number of galaxies in a co-moving volume, which you can now compute, it's a complicated expression, don't worry about it, just observe that it also involves H0 and Q0 and the number of galaxies in some redshift interval as a function of the redshift interval. This is a cosmological test you can do to try to determine these cosmological parameters. Or you could ask for the angular diameter distance. You could say if there is a standard ruler in cosmology, if I move it in redshift, how does it look in terms of its the effective angle that it subtends, right? So that is given by this expression here, and this was actually first applied to the angular extent of radio sources by Kellerman and others, right? This was done by Lowe and Spiller using number counts of galaxies. They were at Princeton, and they actually inferred that omega was 1, lambda was 0. So we can see why that inference was not right, because observe this possibility. If the luminosity of the object that I have just called L, and I said it's absolute luminosity, and you might ask, is that really constant in time? Don't galaxies change with time? Don't they emit more or less light? Yes, in principle they could, right? We have to have a detailed and in-depth understanding of galaxy evolution, which we don't have even now. So let me consider a very small possible dependence that L goes as L0 plus some term linear in time. The galaxy is getting brighter in time. Okay, I could imagine complicating this. I could have a quadratic term, an exponential term, whatever, right? Obviously, observationally, you have to determine what these are. What that means is that the apparent luminosity, according to the equations I've written out before, will not now just be this part here, but have an extra term that alpha is the coefficient of the linear term that will come in there. Okay. So now you see the problem. If galaxies actually evolved in time, but I don't know that, and I assume that they have constant luminosity, and if I use this standard cosmology to try to interpret the observations, to try to infer Q0, I'll go wrong, because I'm not allowing for the fact that there is another term here of opposite sign. I'm not corrected for that, so the answer I get for Q0 may not be correct, right? And this is a trivial example of, just to illustrate to you in a very simple example, how luminosity evolution can bias your conclusion. So this is why the great program of cosmology up to the 80s actually failed, because people became more and more conscious that evolution was a problem, that this actually was a serious problem for inferring cosmological parameters. They had to understand better the astrophysics of what was going on before they could use these things as cosmological probes, right? And in fact, I refer you to some reviews. This is by Peebles and Ratra, Bharat Ratra, Varun Sahani and Stravinsky. They give many examples in their reviews of when people use various cosmological probes, galaxy counts, radio sources, etc. And Patrick did his work on partly on this thing. So you can bias your conclusion if you don't know what their intrinsic evolution is. Okay, so in the sorry, I have to speed through this a little bit, but let me come to the sort of modern day. So recently, it has been possible to detect very, very bright objects, type 1 supernovae, which are basically giant thermonuclear bombs. It's a whole star exploding like a hydrogen bomb. Not core collapse through gravity, but explosion. And it is, they're referred to as standard candles, the idea being that their intrinsic luminosity doesn't actually vary too much. So you can actually use them as distance markers and calibrate them if they go off in a galaxy with a known distance. So for example, M100, which is the farthest galaxy about 30 megaparsecs away, in which we can identify a Cepheid variable with the Hubble Key Project telescope, with the Hubble telescope, that actually had a supernova go off, and using that we can calibrate that and then go further out. And when we go further out, you have seen these plots before, two teams claimed that this diagram of the magnitude versus the redshift, and by now you know what this relationship should be for different geometries. I've given you all the expressions. They claimed that this was consistent with, well, again, the lines are not visible. I'm sorry, this, I think this projector bulb is too strong or something. It's washing out. So this is a line which corresponds to an universe which is expanding at roughly a constant rate. And this is the decelerating universe, and below here, and this is a universe that is expanding, which is become dominated by cosmological constant and is accelerating. And actually you can see that better here. This is the universe expanding at constant rate. This is the universe that is decelerating, and this is the universe that is accelerating. And the claim is that the data favor the top line rather than the middle line or the bottom line. Okay. And that is how they're interpreted, that the expansion rate is accelerating as if driven by a cosmological constant term. Okay. And in fact, the inference is that if you plot the scale factor as a function of time, we are here today, we are not actually looking, we are not measuring the time when the light was emitted, we are measuring the redshift. The redshift is the proxy for time. So these observations are actually being made at one instant in time. Normally to measure acceleration, you need 2 instants of time, and you measure the velocity at those 2 points. Okay? All these observations are at one point in time, but you use redshift as a proxy for the time. Okay? Now, this then implies a cosmological constant whose value in absolute terms is of about twice the present day Hubble parameter. So omega lambda I showed you is lambda over 3 h naught square. So omega lambda of order 1 means lambda is of order h naught square. That is the only scale in the problem, h naught, that has got some dimensions. You know, whatever, kilometers per second, it's got dimensions of inverse time, right? And therefore of energy. Sorry, dimensions of energy in energy units for a particle physicist, it's 10 to the minus 42 GeV today. It's not a scale in fundamental physics. And that then implies, of course, omega lambda is 2 over 3, so about 0.7, right? And this plot which shows that observations of the supernovae, which defines this uncertainty here, when combined with observations of the cosmic microwave background, pick out this point as the solution, and other observations like the baryon acoustic oscillations are consistent with that, and they give us the standard universe of, omega lambda of 0.7, omega matter of 0.3, and the ratio of the pressure to the energy density defines the equation of state. It would be -1 for a cosmological constant, and the statement is that all this data is consistent with W being -1, although the observers allow W to vary to some arbitrary value, including values more negative than -1, which actually can be quite unphysical. But well, even so, the results seem to be all consistent, as you remarked, somebody remarked earlier, with a cosmological constant. Now, what I want to emphasize is that this is entirely inferred from the luminosity Hubble the diagram of supernovae. We don't actually have any direct evidence for negative pressure. We have no evidence that the dominant fluid in the universe, which makes up about 2/3 or even 3/4 in some estimates of the energy density, actually has negative pressure. To measure that, you'll have to see its effect on the formation of structure. It should stop structure from collapsing once it comes to dominate, and this gives rise to something called the late integrated Sachs-Wolf effect, for which there is no evidence. And in fact, since you asked about it, I put in a slide about this earlier. This is the biggest catalogue of supernovae so far assembled, and as I pointed out earlier, it's actually very thinly scattered on the sky. There are large patches of the sky which have not been surveyed at all. But among these supernovae, which now considered add up to about 740, if I actually do the analysis of the data without adjusting uncertainties in a way so as to get assuming the model that I'm supposed to test, then in fact the evidence is actually quite marginal. It is less than 3 standard deviations, as you see here. This is the universe line that separates acceleration from deceleration, and the data are quite consistent. In fact, it's better to look at Q naught. This is the value of Q naught, which follows from the 740 supernovae. So it is, the central value is negative, but there is a significant tail going on to positive values, and the probability that Q naught is actually in this part rather than here is, well, less than 3 sigma. Okay? So it is 99.7% certain that it is positive, but with a small probability it could be, it is negative, but with a small probability it could be positive. And that is about the same probability with which we showed this morning that there is a dipole in the radio galaxies which is 3 times bigger than the CMB, which I discounted because that's not enough. Yeah. Yes? all we did was not to adjust the error bars to get a chi-square of 1 per degree of freedom for the fit to the assumed lambda CDM model. That is all. So the thing that you normally see where this banana is a bit up here, right? That is obtained when they adjust the uncertainties of each data point until they get a fit of chi-square of 1 per degree of freedom, which is the best fit you can get, to the assumed model. So in fact, they're assuming the answer. If you don't assume the answer, if you use instead maximum likelihood, then you get this. Okay.
So you didn't use Bayesian, you used
Sorry?
you didn't use Bayesian.
This is frequentist, but you can do the same thing with the Bayesian analysis that has been done by Roberto Trotta and collaborators. They get the same answer. So I should press on because you're. I'll take questions on this, but let me finish my talk first. So just to give you an example of this, I told you about this Lemaitre-Tolman-Morny metric. So Lemaitre-Tolman-Morny metric, I now have an arbitrary function of r that is multiplying the radial part. Okay. So now I have two different Hubble parameters. One is capital A dot by A, which is this factor here, and the other one has to do with this A prime, which is the that is the A here. And A prime is the factor that is the arbitrary function that is multiplying dr, right? And in fact, I can modify then the Hubble, the Friedmann equation to have two terms. And so this is an example of what a Lemaitre-Tolman-Morny metric would look like around us. We would have to be in the center of a void, okay, with a particular matter distribution around us. And then the luminosity distance is altered accordingly if you solve the Friedmann equation. And you see, you can easily then, for example, have a line which is coincident with the lambda CDM line. Okay, in fact, so close that you can't actually tell the difference. The data are perfectly consistent with both, because you have added one extra degree of freedom, so you can adjust the bright luminosity distances accordingly. Now, I must emphasize this is a toy model. I'm not suggesting that we are exactly at the center of a symmetrical void. This is just to illustrate that a possible radial dependence of the metric, which might be there according to exactly where we are in that complicated matter distribution that seems to be our real universe, can in principle mimic the effect of a cosmological constant in an assumed universe which is exactly homogeneous and isotropic everywhere. So this is why I find this criticism that the LTV metric puts us in a special point and violates the Copernican principle a bit disingenuous, because in the FRW metric, every point is special because every point is equivalent. Okay. Here we are just saying that we are living in an inhomogeneous universe. Maybe you are in the middle of a void, and in fact, the data suggests that we are in the middle of a void, although of course not exactly symmetrically at the center of it. How do you make progress? Well, this is coming. This is what I'll end on. So I'll just show you, explain to you. This is what you can look forward to, because it will take until 2035, and I may no longer be in the business, but you will be there, right? So I emphasized that the measurement of acceleration really requires measurement at 2 points in time. The redshift of an object is not constant with time; it is changing with time. Okay? How much is it changing? Well, the universe is about 10 to the 10 years old, so per year something will change at the rate of 10 to the minus 10 per year. You know, modulo some numerical factor, of course. So that is too small for the redshift. You can't measure a shift of the redshift by 1 part in 10 to the 10. But if you wait 10 years, 15 years, it's 1 part in 10 to the 9. If you take 100 objects and stack them up, improve the signal to noise, you can make it 1 in 10 to the 8. And then this guy can measure it. This is called a laser comb. Okay? It actually won the Nobel Prize shortly after the award of the Nobel Prize for cosmic acceleration. It can measure a shift in a wavelength of 1 part in 10 to the 8, and the idea is to put this object at the in this big telescope that is right now being constructed in Chile, the extremely large telescope, which will monitor not galaxies but the Lyman alpha forest. These are absorption lines due to hydrogen in the spectra of a distant quasar, and if you look at few hundred such objects, then of course they have internal motions, all kinds of random velocities. But by constructing a assemblage of data from many such objects, you can take out all that internal stuff and just ask whereas on the whole the redshift is changing, right? and you expect it to change by 1 part in 10 to the 8, and although you can't see from the back, this is actually showing that the change you're looking for is of the order of centimeters per second for objects which are receding with velocities like 20,000 kilometers per second. I mean, it's fantastic, right? But the simulation of this shows that this is the lambda CDM universe, this is the decelerating universe, this is the universe which is expanding at roughly power law at a constant rate, and the error bars that are expected from this observation are about this size. So although this simulation assumed the lambda CDM model, you can easily see that if it was a different cosmology, it can actually tell the difference in principle. So this is what one might call real-time cosmology, right? So we are not taking a frozen snapshot of the universe and trying to infer everything in terms of models. We are actually exploring the time dimension dynamically, because we are of course traveling in time. We can't help it, right? So I just make a measurement today, I make a measurement next year, by after, and by observing how things evolve real time, I can actually get a handle on cosmology, which Alan Sandage knew about. He first talked about this called the redshift drift way back in whatever 1960 something, and he said it would be impossible to measure. Much the same way that Einstein thought gravitational waves would be impossible to measure. We have seen that happen, and this will also happen. And that, I think, will really open a new chapter in cosmology, so we can really start exploring how to expand beyond what we have been living with since 1932. Right. So I'll stop here now and take questions. Sorry to go over a bit of time.
So this model that you suggested in the previous slides,
Yes.
have you worked further with it, or was
The
it just
LTB
a
model.
to
No, because the LTB model is a toy model. It is just to make a point that
you can mimic a cosmos?
you can mimic it by a radial dependence in the metric, which is not unjustified, given that we do seem to live in a locally inhomogeneous space, right? But there are many other ways you can think about that. So in principle, you could use a so-called Zacharias metric, which is anisotropic as well as inhomogeneous, and people have done that. The problem, of course, is that once you start adding parameters, then it becomes then there is not enough data to really fix every parameter. So someone was asking earlier about information criteria. So the rough rule of thumb is that if you add n new variables, you should take 2 times n away from your chi-square. Okay. So in other words, adding the degree of freedom, extra thing, should actually improve your chi-square better than at least twice that. So this is a rule of thumb. Strictly speaking, you should do a proper Monte Carlo Bayesian analysis, right? But roughly this works. So in this case, we are adding a arbitrary radial function. All I'm saying is that an arbitrary radial function seems arbitrary. I'm using the term myself. But actually, it is whatever nature has decided. There is some radial function near us. So the question is, can that radial function in fact mimic the effect of acceleration? I don't know the answer, because to do that, first of all, I have to ask, is the data uniform on the sky? It clearly isn't. It's only in some directions.
So what about using simulations to fix these parameters? Maybe you can derive a power spectrum from
Yeah, good point. So if you can do a constrained simulation of the universe, which ends up looking like the slide I actually started with, so people can actually do that. When you do n-body simulations, you can actually choose your phases such that you end up in an universe that actually looks like the one that we live in, right?
So the phases of your initial distribution.
That's right. Yeah. So it's difficult because then you can't normally get the resolution necessary to see something of this scale.
Right.
So this is down to, this is about 30 megaparsecs. It's resolving down to. That is hard to do. But in principle, you could do a simulation, and actually, that is one aspect. The second aspect is that all simulations that have been done to date are Newtonian. They have not taken generativistic effects into account.
Yeah, but the growth factor will get modified according to the metric.
That's correct.
Right.
So there are several aspects. One is the GR effects, which will actually allow you to take account of the back reaction of the growth of structure on the metric. Then there is the question of whether there are selection effects according to what direction the surveys are looking at. But you can get around the third factor, which I had mentioned here, which is where we are actually located, which is this cosmic variance. Are all observers the same? Clearly not. We are right here. We are not there. That you can get around by doing what you suggest. By doing a constraint simulation and asking, in this universe, if I were to look at supernovae in these directions, what kind of a Hubble diagram would I see? That would be the right thing to do.
I think Julian Adamek and Rod Euler built relativistic simulations for recent.
That's right. They have just started. So there are three groups. That group is one. Then there is one based around Geneva and Queen Mary at the moment now, and a third group in the U.S. at whatever it's called. Anyway, so there are three groups of people, but they have just started doing it, and they don't agree with each other. That's another direction to go. So all these questions I'm raising are being addressed by some people, but they are not the mainstream yet. Come on, I've said at least 20 provocative things, so please ask at least one question. Yeah? Yeah.
So you mentioned you can get lambda from a surface term. I didn't really get how.
Oh, that was no. I explained to you how Einstein had constructed his static universe. So he just in that example, he just chose it to make A static. You just have you have an equation for A double dot by A, and you just want the right hand side to be 0. So you can then choose in that solution the value of lambda such that it exactly cancels out the other part and you have 0, and then that actually defines the radius for the universe. But that is not a physical solution, because that solution is unstable to small fluctuations in the metric. So in other words, if I just introduce a density fluctuation or a metric fluctuation, that will grow exponentially without limit. So that space-time will self-destruct.
The cosmological constant, can it come from a surface term?
No, this is related to the question that was asked earlier. There have been many attempts to see if the cosmological constant is in fact a surface term or a constant of integration or a Lagrange multiplier. None of these things have any physical significance. All such efforts have actually failed. So there is a interesting review by a student of De Hooft called, I've got the reference somewhere. He collected every attempt made to solve the cosmological constant, of which there are several hundreds, and they all failed. But some of them are very interesting and provide you a lot of insight. And just learning why they fail is also quite interesting. Right? And it's worth studying that. But my short answer to your question is no, it doesn't work. It simply doesn't work. And in particular, the way that you can see it will not work is that the effective cosmological constant that is entering Friedmann's equation is not just the geometric part, okay?
Also the field.
Exactly. And the two add together and the two know nothing about each other. Right?
But they have the same physical effects.
They have the same
You
physical
can't
effect.
distinguish
Yeah.
them.
So again, particle physicists also sometimes get the wrong end of the stick. They talk about just the quantum fluctuations part. Reducing that to 0 by some means of saying there's some cancellation mechanism is not going to help you with the geometric part. It is the sum of the two that matters. So there is only one solution to the cosmological constant problem, which particle physicists tried, which did not work, but for an interesting reason, which tried to address precisely this combination, and it is related to something called the, well, I'll come to that later, to the axial problem. There is a strong CP problem in particle physics. There is a term you can add in the standard model Lagrangian that violates CP, okay, in the strong interactions. We observe no such effect. So that term has to be 0. And that term is just like this, a paired term, which is called theta, plus a term that comes from the determinant of the quark mixing matrix, which is the argument of the determinant of the mixing matrix, n. So there are two terms. And the way that the problem is resolved in particle physics is to say, let us make the whole thing a dynamical variable by making it a field. The field can then develop a potential and settle at the bottom of the potential. This is the so-called axiom. And therefore, we can understand why that term does not exist in today's universe. It's 0. The axiom is relaxed to 0 because it got a mass, because it mixes with the pion. There's a whole sort of thing behind it. And we are busy looking for this axiom. This is the only known solution to the strong CP problem. So the authors of that, or one of the authors of that, Peche, he tried the same trick for the cosmological constant. Unfortunately, what happens is that when you try doing that, when you try making lambda plus the contribution from the field into a dynamical field itself, its evolution back reacts on the metric and destroys the solution. So Weinberg actually gave a theorem in his famous review on lambda, which shows that there is no relaxation mechanism possible for lambda in at least in 3 plus 1 dimensions. Because this is the case where the metric cannot be given, taken to be constant, regardless of what drama is being played out on it. It's one of the cast. It is involved in this. The energy density will back react on the metric, and as this quantity that you have defined as a field tries to relax to 0, it will again curve space. So there is no solution to the cosmological constant problem of the kind that solves the axiom, which is a very interesting observation, because of course some people then try to see if they could do it in higher dimensions where the theorem doesn't hold. And it's true, in 5 dimensions you can have a solution in lambda equal to 0, but that solution is not an attractor. There is no reason why it should be there, it should be somewhere else. So maybe that was more than you actually asked, but just to, this is a problem that has taxed the best minds in physics, okay? And there is no solution. Yeah?
Probably these questions are very trivial. I did not understand very properly.
Huh.
When you say that when the cosmological constant was not there in the initial Einstein equation,
Yes.
the solution was not stated. So what does it mean?
No. I said that initially it was not added because it was not recognized that you have to add it whether you like it or not, because it reflects the underlying symmetry. Okay. So underlying Einstein's equation is general coordinate invariance. Right? So that allows you, that means Einstein's equations, you can always add a term which is something multiplying the metric, and that also, so there's an infinite number of possible equations you can write.
My result should be same.
Exactly. So dynamically my result should be the same, and adding that thing to the left does not change the underlying symmetry of the equation. So you must have it. It's not your choice whether you have it or not. Right? But the way it was actually introduced was historically that first Einstein tried to construct a static solution, effectively using the cosmological constant to stabilize the metric from expanding. But that actually is not the way to do it, because it's an unstable solution. And then we gave up the whole thing and tried to make it 0, but you can't make it 0 just because you want to make it 0. Right? So basically you can look at it as either a absolute disaster, okay? Weinberg famously calls it the bone in our throat, which I think is a rather good way of putting it. Or you can see it, as I do, as telling us that we are missing something so truly fundamental that there is plenty of work for you guys to do. Don't think that all of physics is solved. That itself is telling us that something truly deep missing in our present understanding of both gravity and field theory.
And also you mentioned in this talk, in the same concept, that this cosmological constant, that also many field theory textbooks, cosmological constant and the divergence we see in, let's say, scalar field theory, that vacuum state divergence, that is not connected. Can you explain how that should?
Oh, that is just to do with the ground state vacuum fluctuations, which also act like a cosmological constant, right? But in field theory, it is not a problem. You can denormalize it away at every order of perturbation theory, right? Because there is no observable. You can only measure differences in the energy, not the absolute energy. The only thing that measures the absolute energy is gravity. So the problem only arises when you try to couple field theory to gravity. If you don't care about gravity, you can be a happy field theorist. Nobody, I mean, the cosmological constant has no effect on what we do at CERN. Thank God for that. Okay. But it's only when you bring in gravity and you accept general relativity's basic dictum that all energy density couples to gravity, I can't have a choice. So what it is telling us is that there is something very deep that we don't understand about how vacuum energy couples to gravity. And why it should have a special status, I have no idea. But I'm in good company there. Not only does it not couple to gravity, but the sum total of the geometrical part and the energy momentum tensor part doesn't couple to gravity. How they know about each other is another deep question. So of course one can ignore all these very fundamental problems and treat the whole thing very empirically and just say, let me call it, dark energy, give it a general equation of state, and observationally I'll try to constrain all its parameters. And in fact, Einstein and de Sitter agreed that that was the only way to try to determine what it was, right? But actually, what they I think missed is that the way we construct the cosmological model naturally sets a scale for the cosmological constant. It's h naught square. That's the only dimensionful quantity in the theory. And I don't think one needs to be very sophisticated to realize that it is not possible for a fundamental quantity to know at what rate the universe is expanding today. It has to be h naught square, not h square, because then there is no exponential expansion. As you will see, you can just transpose it on the left of the Hubble equation. Okay, so there is something special about our epoch, and this is often called the coincidence problem. But actually, it is not really a coincidence problem, because what is special about our present day epoch is that we are here today making observations. We were not doing that at 1 billion years in the past. But I don't know. I mean, this is a very elaborate discussion, and people have various points of view. I don't want to insult them all, but I think many of those discussions are completely misplaced, because the central question to me is h naught is not a scale in a fundamental theory. And therefore, I cannot see how a fundamental quantity can know how to take that value upon itself. So, this is my concern.
Just below the Einstein de Sitter graph that you showed, there was a yellow graph which was oscillatory between the two. I don't understand that.
Oh, that was the universe where the energy density is high enough to cause the collapse. But you can put a negative cosmological constant that causes a bounce. Because, I should mention that the sign of the cosmological constant is not determined. No field theory can give you either the absolute value or even the sign of it. Okay. All we can argue is order of magnitude. It should be set by the scale of the theory. So standard model will have something of order few hundred GeV to the 4. Right? So in principle, you could have negative lambda. Negative lambda would have the effect of, so one is causing expansion, the other is causing collapse. In principle, you can have a bounce. So depending on the size, so you can just play with Friedman's equation, just put in different values of lambda. Actually, you can code it into Mathematica and see the whole family of solutions. And if you do that, then you would reproduce many of the papers written in the 60s, which actually did just that. Today, you can write a little app to do it. So you could, in principle, have a bouncing cosmology. Of course, the mechanism for the bounce then also you have to then think about. And there is actually some interest today in bouncing cosmologies for other reasons, because this also relates to the question of, are we a one-shot affair, or is there something cyclic about the universe? That always then brings up questions like, did we, in fact, can we emerge from a singularity, from a previous universe? That seems to be very, very difficult with generating perturbations. But in many ways, an expanding, accelerating phase can actually look exactly the same as a collapsing, decelerating phase with regard to generation of perturbations. The two are scale invariant. Okay? And this has been used by various people like Turok and Steinhardt and so on to try to construct cosmologies where we evolved from a previous universe into this one. But in every model that has written down to do with, which has involves the present day acceleration, you have to introduce the parameter h naught by hand, 10 to the minus 42 GeV. Whatever you call it, quintessence, phantom energy, blah blah, always have to put in that scale by hand. It is not a natural scale. And so in some sense, you can invent a lot of new dynamics, but whether it's relevant or not is determined by the scale of the problem, and the scale is never dynamically generated. It is always put in by hand. So it is right if the person writing that paper knows something that the rest of us don't. Yes.
So you're saying the current value of the Hubble constant does not arise out of the theory?
No,
It has to
no,
be
it
put
has to be
on
put
its
in
own,
by
and
hand.
that's a glaring.
But that is
problem.
the magnitude of the so-called vacuum energy or
Right,
dark
right.
energy or whatever. That
Right.
is what determines it.
Right.
And that is why one wonders whether it could have some other interpretation than energy, because we don't observe it as energy. We observe it as a change of observables like luminosity distance or angular diameter distance, and I showed you the expressions for all that. From that you infer something. So if you go wrong in that inference, then the value that you
values-
get is it doesn't reflect a genuine physical phenomenon. The next test would be to then say, supposing it is genuinely physical, what would I predict that then can be used to falsify it? And there are such tests. So, for example, if it is really something with a negative pressure, it should affect the formation of structure.
Right.
And in principle, then you should see, once it comes to dominate, which is at about redshift of 1, below that, structure instead of collapsing should stop collapsing, okay, and bound structure should even start to break up if given enough time. This will induce a corresponding effect on the microwave background photons which are propagating through a structure. So if there is some potential well, a photon falls into it and climbs out, the two normally cancel each other, but if the potential well itself is evolving as the photon crosses it, then they don't, and then you see this so-called integrated Sachs-Wolf effect. Now, this has been looked for, but nobody has seen it for the very good reason that you need about, there was an estimate made by Afshordi, you need 10 million galaxies with well-measured redshifts to a precision of 0.05 to see this effect. So far, we don't have that. We have maybe 1 million with that precision. So, when we have measured 10 million galaxies, then we'll be able to see if this thing is there. But the problem is that meanwhile, everybody knows the answer. So even with a subset of data, even with data which is not that accurate,
You have a sort of bias.
well, it's like doing an undergraduate lab experiment. You're not
Yeah,
going
you
to
know
give me
the
a speed
answer.
of light which is 3 times off the correct value because you know it, don't
Yeah,
you? Yes? Is there a question? No.
Maybe we break for
Yeah, let's break for tea now. Thanks.